Ave Coders, and welcome to the tutorial on logistic regression. The basis of logistic regression is of course a function that is called a logistic function. But this function also has a more scientific name such as a sigmoid, and it was developed in order to describe the growth of populations in various ecosystems. The function is an S-shaped curve that essentially takes any real number and converts it to a value between 0 and 1. By the way, here's the formula, where e is the basis of the natural logarithm or the Euler number. Here is an example of the equation describing the logistic regression. If you watched my lesson on linear regression, then you probably can recognize our old friends. Beta 0, this is an intersection, and beta 1 is the coefficient of the input value x1, and the output value which we're trying to predict is defined as y, but this time the difference is that the output value will be mapped to a binary value, either 0 or 1. In other words, based on the set of values of the independent variables x, we will try to calculate the probability that the dependent variable y will take the value 0, which can be explained as the event did not occur, or 1, that is, the event occurred. The values of the logistic regression coefficients, the betas, will be calculated from our training data. This is usually done using the maximum likelihood estimation method. I plan to cover maximum likelihood estimation in a course on statistical methods in machine learning. There will also be a separate course on the minimal math that is necessary to understand what is going on here, and other fun and useful stuff. Therefore, in this introductory video, we'll learn first of all how to put it all into practice using the Scikit Learn Library. So for now, just take it easy and don't worry about the overwhelming math and quirky statistical methods. You can find the link to this Colab notebook in the description, and bear in mind that we've already cleaned our features and binarized them, so with the help of the Scikit Learn Library, this should be a walk in the park. The first cell contains all libraries and modules that we've already used in our previous lessons, so I've just copied and pasted them. So let's just run this cell and import them. And we also need to mount our drive to access the data, so a few more imports required. Now we can run these cells as well. And once you'll click allow for the permission, we will have an access to our data, which we've saved as well in our previous lessons. So it is nicely broken down into our training, validation, and test sets. So let me just copy that code from our lesson on the complete machine learning pipeline. Here it is. To make this lesson a bit shorter and concise, I'll be only using training and test features and training and test labels, of course. So now we are ready to fit our logistic regression model provided by the Scikit Learn Library to our data. But before we'll do that, let me illustrate something. So in essence, the logistic regression model will digest all the data and will try to predict the outcome, whether the passenger will survive or not. Therefore, 1 is going to be for survival and 0 is going to be for the unfortunate outcome. So let's take the training labels, for example, to represent the expected output of our model. So these are the outcomes known to the model. In fact, the model was trained on this data. So in essence, the model went through all this training data, combinations of different features, and then it was shown to what kind of outcome they can lead to. So for illustration, these training labels were loaded into the Seaborn count plot. And as you can see, we have 2 bins, 0 and 1. So now what we're going to do, we're going to take this model and we're going to give it the test data. So the data that it has never seen before. So first of all, let's define our model. I'll save it into log reg. So this is logistic regression from the Scikit Learn. No other parameters. Now we'll fit this model to our training data. So it will learn the patterns within this data. So log reg.fit, and I'll be copying the train features and train labels. And after we fit this logistic regression model on the training data, next we'll try to use it for predictions on our test data. But first of all, we'll use the score method from the Scikit Learn Library that returns the mean accuracy on the given test data and labels to check how our model is doing, what to expect, what kind of accuracy can we expect from our model on this test data. So as an input to this score method, I will use the test features and test labels. So I'll just copy them from that cell. So let's check the score. It's 0.775, so not too bad. This means that on average, we can expect that our model will be right in 0.775 cases. Or in other words, roughly 77% of our predictions will be correct. Okay, so now we can make predictions, and to do so, we will be utilizing the method from Scikit Learn Library called predict that predicts class labels for samples in our X or test data. So we'll save the outcome to the survival variable, and this predict method will only take one argument, which is going to be the test features, and we'll try to predict the test labels. Okay, to check how well our model predicts, let's write a few simple print statements. I will label the outcomes as OK and not OK. So OK will stand for a passenger survived, and it will be equal to all outcomes where the value is not equal to 0. So some survival not equal to 0. Similarly, not OK will stand for the outcomes where passenger didn't survive, and it will be the sum of all outcomes equal to 0. Now let's run the cell and check for predictions. So we predict that 59 passengers from the test data set will survive, and 119 were unlucky. And we already know that 77% of the cases are correct. Now, let's talk about the efficiency of our algorithm. In particular, a certain table, or rather a matrix that is used for its visualization, which came to machine learning from the field of statistics and is called the confusion matrix. Basically, it depicts how accurately our algorithm predicted the outcome of an event. Horizontally, it represents our model's predictions, and vertically, the real outcome of the event. 1 means that the passengers survived, and 0 that they did not. So the intersection of two ones gives us true positive results, meaning we predicted that the passenger would survive, and they survived. The intersection of 0 and 1, the lower left quadrant, gives us false negative results, and means that we predicted that the passenger would not survive, but they actually managed. The upper right quadrant is responsible for the false positive results. That is, we predicted that the passenger will survive, but in reality the passenger didn't survive. And finally, the upper left quadrant, true negative results. That is, the model predicted that the passenger will not survive, and indeed they didn't make it. So we import this confusion matrix from sklearn.metrics, and now we can define it in a new cell. I'll name it conf mx, will be equal to confusion matrix, and we'll use it to visualize our model's predictions against the expectations, so the true test labels. And to plot these figures, we'll once again turn to the Seaborn library, but this time we'll use the heat map. So as before, seaborn.heatmap. And we'll specify a few parameters. First of all, it will take our conf mx as the data to plot. Also, we'll specify that annotation will be equal to true. FMT is a string formatting code that is used when we are adding the annotations. CMAP is an optional parameter for matplotlib column map, name or object. In this case, we're going to be using the crest column map. We're going to specify the title for our heat map as the confusion matrix, and we'll make the size of this title equal to, let's say, 12. And after we've done that, on the last line, we'll write conf mx to see the original representation of the confusion matrix object. So above the nice looking heat map, you see we have this confusion matrix represented as an array, and here is our heat map. So we have 42 of the true positives, 96 of the true negatives, 17 false positives, and 23 represents false negatives. The Scikit Learn Library turns working with logistic regression into an easy and enjoyable process. But when working with any data, you should always remember that the data can tell us more than a simple binary outcome. And there will be a separate video about this. I will go to the cemetery where some passengers from the Titanic are buried, and we will try to possibly establish whether we can extract some stories told by the data we have on these people to maybe learn about their fate in this horrific maritime tragedy. So I definitely recommend you to subscribe to the channel and press the notification bell so you won't miss this exceptional data science travel video. That was V. Please give this video Emperor's thumbs up, and I'll see you in the next video. Bye for now.